Welcome to Lyons Township High School AP Physics. Today we've got an example involving Newton's second law. It's a pretty straightforward example. We have a sled and we're pulling the sled along the snow and with a force P for pull. You can name that anything you want. And we have some data. The sled has a mass of 60 kilograms. That would be either a couple really small kids or one pretty big kid. I'm about 78 kilograms, so it'd be like almost like me on there. Somebody's pulling with 200 newtons of force, which is 45 pounds or so, 40 pounds. Mu sub k is 0.2, so that's the coefficient of friction. And the angle of that the rope makes with the horizontal is 30 degrees. So if you need a second, pause the video and make sure you copy all that down. All right. So here's what we're going to do. We're going to determine the following things about our sled. We're going to determine the normal force acting on the sled, the force of friction acting on the sled, and the acceleration of the sled as the person pulls on it, okay? So the first step is to draw an FBD. Now, we're actually going to draw two FBDs, all right? So the first FBD would be what I would call the College Board FBD. They literally want to know exactly how many forces act on the sled and exactly which direction they point. So here's our sled. We're going to use a dot. Now, I always start with gravity. That always pulls down. The weight of the sled always pulls down. So there we go. We got that. That's mg. Okay. And then basically anything that touches or rubs on the sled is going to cause a force. So we have P. All right. So there that is at an angle. All right. We have the snow or the ground pushing up on the sled. That is F normal. Okay. And then the sled is rubbing against the snow. That's your friction. And that is kinetic friction because the sled is sliding over the snow. So there's your FBD. There's four forces acting on the sled, and there they are. The next thing we're going to do is we're going to draw a second FBD. And that one, we're going to split all the forces up into two directions. We're going to split them up into components that are parallel to the motion and perpendicular to the motion. And virtually every problem that we do involving forces, that's how we're going to do it. We're going to say, hey, which way is the thing moving at that moment in time? We're going to find which forces act parallel and which acts perpendicular. If a force doesn't act perpendicular nor parallel, we're going to find the parallel and perpendicular components of that force to the motion. So this sled is moving to the right. So we have the horizontal and we have the vertical. Okay? So let me redraw this over here. Now you'll note that Fn and mg are both perpendicular to motion. I ain't got to do anything with those. And F force of friction is parallel to the motion, so I don't got to do anything with that. So I'll just redraw those three forces right after that. We got Fn, we've got mg, and we've got force of friction. But P, the pull doesn't act parallel, nor does it act perpendicular to this direction of motion. Okay, so here's what we're going to do. We're going to split that up into components. Now that force P has a parallel component. That's this component here. If you imagine this little right triangle right here, we're looking at the adjacent leg of this little right triangle. We have the hypotenuse. We want the adjacent leg. What trig function goes with those two, hypotenuse and adjacent leg? That's cosine. So it turns out that this component is P cosine of the angle. Okay? Now, a quick note. Is the normal force going to equal mg here? No way. The normal force is not going to be mg. Okay, now next question. Will the normal force be more or less than mg? Okay, so make your guess. We're going to calculate in a second. We'll get a number in a sec, but make your guess. Should Fn be more, equal to, or less than mg? Well, I just told you it's not equal to, so is it more or less than mg? Well, we've got a vertical component of P we got to add in this diagram. That's this little leg of the triangle right here, which is the opposite leg to that angle. Opposite is sine. So this, I always put the arrow right there. This is P sine of the angle. Okay, so now we've got two directions to analyze. We have the horizontal direction and the vertical direction. I will start with the vertical direction. So the net force in the perpendicular to the motion direction equals ma perpendicular. Now, question for all of you. What is the vertical acceleration of the sled? I hope you didn't say 9.8, all right? This sled is moving horizontally. It doesn't have any vertical acceleration, so this equals 0, okay? Well, how many vertical forces do we have in this diagram? Well, we've got 3. I will use a coordinate system. I'll say up and right are positive. So I got 2 up forces and 1 down force, so I'll put them in here. So we've got F normal plus P sine theta minus mg equals 0. And I've got all the numbers but Fn, okay? So Fn equals, now I'll rewrite this. I'll put these over here and I got to reverse their signs, so it becomes mg minus P sine theta. So notice that Fn is going to be less than mg, right? It's going to be mg minus this thing. Okay, and if you plug your numbers in, let's see, this equals 60 times 9.8 minus 200 sine of 30, which equals 588 minus 100. This equals 488 newtons. Now, I went ahead and wrote these out for a couple reasons. One, if I mess up my work, I can fix it real easy, just go and erase something. But I'm going to actually change something up in a minute, and I'm going to have you guys observe if we change something, what happens, okay? Now, the other thing we asked for the force of friction. I'm going to do that. I'll do it right here, okay? So force of friction is mu Fn, which is mu, no, not mu mg. That's mu times the 488. And in the problem, I said mu is 0.2. So if you take 0.2 times 488, you get 97.6. 97.6 newtons. Now, quick note, if this force is bigger than this force, the thing is not going to accelerate. Matter of fact, it would be slowing down or it wouldn't be moving. Okay? So now we're going to look and figure out the acceleration. So we're going to do net force in the parallel to the motion direction equals ma parallel. We said right's positive, so we got P cosine theta minus ff equals ma. Now, I know this number is 97.6, but I'm not going to put that in here yet, and I'm going to show you why in a minute, okay? So I'm going to continue this in the next board. We've got P cosine theta minus friction is mu Fn, and that equals ma. And so we've got P cosine theta minus mu, and then what was Fn? I'm gonna put the expression in there, and I want to explain why in a sec. So we got mg minus P sine theta. That's our normal force, and that all equals ma. So I'm subbing in for Fn right there. Now I've got values. So P is 200 cosine of 30 minus mu, which is 0.2 times 60 times 9.8 minus 200 sine of 30 equals m, which was 60 times a. This here is about 173 minus. Now, check it out. We got 0.2 times, this is 588 minus 100 equals 68. Now, you might be wondering why I'm still keeping these separate. Okay, I got a reason. Now, if you're just solving the problem, you know, you can just plug all the numbers in, you're going to get the answer for A, but I'm drawing it out for a reason. All right, so then we got 173 minus, I get, 97.6 is what we got before, right? Equals 60A, and A will be, I got 1.26 meters per second when I did my calculation, okay? So, that's the acceleration of the sled. Now, a quick note, notice the normal force, which is 488, was less than the weight, which is 588, okay? A couple quick notes about the problem in general. I draw two FBDs. I draw what forces act and in which direction they act, and then I split them up into perpendicular and parallel components to the motion, okay? Then you look at the perpendicular and the parallel to the motion direction, and that force equals ma. If you split it up this way, the perpendicular acceleration should be 0 because, hey, that sled's moving to the right. Therefore, there isn't an upward acceleration, and you can usually use that fact to figure something out. Now, here's why I kept all that work out there. What if your friend who's pulling you, let's say, instead of pulling up on you at a 30-degree angle, let's say they got behind you and they push down at 30 degrees as you go. What would happen to the normal force and your acceleration? Okay. Well, since we've got friction, and that's a big if, because we have friction, several things are going to happen. Okay. If your friend was pushing down on you, this FBD, what would change would be P would point down and to the right, and this little guy, P sine theta, would point down. So that would be your one change. So over here, you'd have a minus, and I'll do this in red. You'd have a minus P sine theta. This would become a plus, and a plus, and a plus, and you would get 688 for your normal force. Okay? And then this wouldn't change at all yet. Same, aha, this would become a plus, this would become a plus, this would become a plus. This number would get bigger, okay? So we'd have 173 minus a bigger number, which would give us a smaller net force. So since we would have a smaller net force, we would have a smaller acceleration, okay? Now that is if there's friction. If there's friction, the acceleration would be smaller. What if there was no friction? All right, what if this was perfectly smooth ice and there was zero friction? Would it matter if your friend pulled up on you or pushed down on you at that 30-degree angle? Well, if you did that, this force is gone and gone. Friction's gone, okay? Whether they pulled up or down, you'd have either what's in black or what's in red, okay? So that wouldn't change. But over here, it would just be, there's no friction. So it'd just be P cosine theta equals ma. Well, in this case, does the normal force affect the acceleration? Well, since there's no friction, the normal force doesn't ever show up in this equation. So your acceleration would just be P cosine theta over m. It wouldn't matter if your friend kind of pulled up at an angle on you or pushed down at that same angle on you. You'd have the same acceleration. So that answer is different. If you do have friction, you get different accelerations if you push or pull. If there's no friction, you get the same acceleration if you push down or pull up. So I hope that problem was helpful, and thank you very much.